Learning objectives. At the end of this topic, you will be able to cite charged particles in matter, discuss the structure of an atom, explain how electrons are distributed in different orbits, define the valency, atomic number, mass number, and isotopes. Introduction. Sheila and a friend went for a walk.
What makes the atom of one element different from the atom of another element? And 2. Are atoms really indivisible, as proposed by Dalton, or are there smaller constituents inside the atom? I don't know. We shall find out the answers to these questions in this chapter. We will learn about subatomic particles and the various models that have been proposed to explain how these particles are arranged within the atom. Let me tell you more about it in this chapter.
Charged particles in matter. Many scientists contributed in revealing the presence of charged particles in an atom. It was known by 1900 that the atom was not a simple, indivisible particle but contained at least one subatomic particle, the electron, identified by J.J. Thomson. Even before the electron was identified, E. Goldstein in 1886 discovered the presence of new radiations in a gas discharge and called them canal rays. These rays were positively charged radiations, which ultimately led to the discovery of another subatomic particle. This subatomic particle had a charge equal in magnitude but opposite in sign to that of the electron. Its mass was approximately 2000 times as that of the electron. It was given the name of proton. In general, an electron is represented as E- and a proton as P+. The mass of a proton is taken as 1 unit and its charge as +1. The mass of an electron is considered to be negligible and its charge is -1. It seemed highly likely that an atom was composed of protons and electrons mutually balancing their charges. It also appeared that the protons were in the interior of the atom, whereas electrons could easily be peeled off but not protons. The structure of an atom. Thomson's model of an atom. The discovery of two fundamental particles, electrons and protons, inside the atom led to the failure of this aspect of Dalton's atomic theory. It was then considered necessary to know how electrons and protons are arranged within an atom. For explaining this, many scientists proposed various atomic models. J.J. Thomson was the first one to propose a model for the structure of an atom. Thomson proposed the model of an atom. The electrons in a sphere of positive charge were like currants, dry fruits in a spherical Christmas pudding. We can also think of a watermelon. The positive charge in the atom is spread all over, like the red edible part of the watermelon, while the electrons are studded in the positively charged sphere, like the seeds in the watermelon. Thomson proposed that 1. An atom consists of a positively charged sphere and the electrons are embedded in it. 2. The negative and positive charges are equal in magnitude. So, the atom as a whole is electrically neutral. Although Thomson's model explained that atoms are electrically neutral, the results of experiments carried out by other scientists could not be explained by this model. Rutherford's model of an atom. Ernest Rutherford was interested in knowing how the electrons are arranged within an atom. Rutherford designed an experiment for this. In this experiment, fast-moving alpha particles were made to fall on a thin gold foil. Let's look at some of the prominent notifications of the experiment. He selected a gold foil because he wanted as thin a layer as possible. This gold foil was about 1000 atoms thick. Alpha particles are doubly charged helium ions. Since they have a mass of 4U, the fast-moving alpha particles have a considerable amount of energy. It was expected that alpha particles would be deflected by the subatomic particles in the gold atoms. Since the alpha particles were much heavier than the protons, he did not expect to see large deflections. But the alpha particle scattering experiment gave totally unexpected results. Let's discuss the observations of the experiment. Most of the fast-moving alpha particles passed straight through the gold foil. Some of the alpha particles were deflected by the foil by small angles. Surprisingly, 1 out of every 12,000 particles appeared to rebound. On the basis of his experiment, Rutherford put forward the nuclear model of an atom. There is a positively charged center in an atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. The electrons revolve around the nucleus in circular paths. The size of the nucleus is very small as compared to the size of the atom. Let's discuss the drawbacks of Rutherford's model of the atom. The revolution of the electron in a circular orbit is not expected to be stable. Any particle in a circular orbit would undergo acceleration. During acceleration, charged particles would radiate energy. Thus, the revolving electron would lose energy and finally fall into the nucleus. If this were so, the atom should be highly unstable, and hence matter would not exist in the form that we know. We know that atoms are quite stable. Bohr's model of an atom. In order to overcome the objections raised against Rutherford's model of the atom, Niels Bohr put forward some postulates about the model of an atom. They are: only certain special orbits known as discrete orbits of electrons are allowed inside the atom. While revolving in discrete orbits, the electrons do not radiate energy. These orbits or shells are called energy levels. Energy level in an atom is shown in these orbits or shells are represented by the letters K, L, M, N, and so on, or the numbers n is equal to 1, 2, 3, 4, and so on. Neutrons. In 1932, J. Chadwick discovered another subatomic particle which had no charge and a mass nearly equal to that of a proton. It was eventually named as neutron. Neutrons are present in the nucleus of all atoms except hydrogen. In general, a neutron is represented as small n. The mass of an atom is therefore given by the sum of the masses of protons and neutrons present in the nucleus. How are electrons distributed in different orbits, shells? The distribution of electrons into different orbits of an atom was suggested by Bohr and Berry. The following rules are followed for writing the number of electrons in different energy levels or shells. 1. The maximum number of electrons present in a shell is given by the formula 2n square, where n is the orbit number or energy level index, 1, 2, 3, and so on. Hence, the maximum number of electrons in different shells are as follows. First orbit or K shell will be 2 into 1 square is equal to 2. Second orbit or L shell will be 2 into 2 square, that's equal to 8. Third orbit or M shell shall be 2 into 3 square, that's equal to 18. Fourth orbit or N shell will be 2 into 4 square, that's equal to 32, and so on. 2. The maximum number of electrons that can be accommodated in the outermost orbit is 8. 3. Electrons are not accommodated in a given shell unless the inner shells are filled. That is, the shells are filled in a stepwise manner. Atomic structure of the first 18 elements is shown schematically in the figure. Valency. We have learnt how the electrons in an atom are arranged in different shells or orbits. The electrons present in the outermost shell of an atom are known as valence electrons. From the Bohr-Berry scheme, we also know that the outermost shell of an atom can accommodate a maximum of 8 electrons. It was observed that the atoms of elements having a completely filled outermost shell show little chemical activity. In other words, their combining capacity or valency is 0. Of these inert elements, the helium atom has 2 electrons in its outermost shell, and all other elements have atoms with 8 electrons in the outermost shell. And all other elements have atoms with 8 electrons in the outermost shell. The combining capacity of the atoms of other elements, that is, their tendency to react and form molecules with atoms of the same or different elements was thus explained as an attempt to attain a fully filled outermost shell. An outermost shell, which had 8 electrons, was said to possess an octet. Atoms would thus react so as to achieve an octet in the outermost shell. This was done by sharing, gaining, or losing electrons. The number of electrons gained, lost, or shared so as to make the octet of electrons in the outermost shell gives us directly the combining capacity of the element, that is, the valency. Atomic number and mass number. Atomic number. We know that protons are present in the nucleus of an atom. It is the number of protons of an atom which determines its atomic number. It is denoted by Z. All atoms of an element have the same atomic number, Z. In fact, elements are defined by the number of protons they possess. For hydrogen, Z is equal to 1 because in hydrogen atom only one proton is present in the nucleus. Similarly, for carbon, Z is equal to 6. Therefore, the atomic number is defined as the total number of protons present in the nucleus of an atom. Mass number. After studying the properties of the subatomic particles of an atom, we can conclude that mass of an atom is practically due to protons and neutrons alone. These are present in the nucleus of an atom. Hence, protons and neutrons are also called nucleons. Therefore, the mass of an atom resides in its nucleus. For example, mass of carbon is 12U because it has 6 protons and 6 neutrons. 6U plus 6U equal to 12U. The mass number is defined as the sum of the total number of protons and neutrons present in the nucleus of an atom. Isotopes. In nature, a number of atoms of some elements have been identified, which have the same atomic number but different mass numbers. For example, take the case of hydrogen atom. It has 3 atomic species, namely protium, deuterium, and tritium. The atomic number of each one is 1, but the mass number is 1, 2, and 3 respectively. Other such examples are 1. Carbon, 12C, subscript 6, 14C, subscript 6. 2. Chlorine, 35Cl17 and 37Cl17, etc. 35Cl subscript 17 and 37Cl subscript 17, etc. On the basis of these examples, isotopes are defined as the atoms of the same element having the same atomic number but different mass numbers. Therefore, we can say that there are 3 isotopes of hydrogen atom, namely protium, deuterium, and tritium. Let's discuss the applications of isotopes. Since the chemical properties of all the isotopes of an element are the same, normally we are not concerned about taking a mixture. But some isotopes have special properties which find them useful in various fields. Some of them are: an isotope of uranium is used as a fuel in nuclear reactors. An isotope of cobalt is used in the treatment of cancer. An isotope of iodine is used in the treatment of goiter. Isobars. Let us consider 2 elements: calcium, atomic number 20, and argon, atomic number 18. The number of electrons in these atoms are different, but the mass number of both these elements is 40. That is, the total number of nucleons is the same in the atoms of this pair of elements. Atoms of different elements with different atomic numbers, which have the same mass number, are known as isobars. Summary. Let's summarize the topic. The mass of an electron is considered to be negligible and its charge is -1. Ernest Rutherford was keen to know the arrangement of electrons within an atom. Niels Bohr put forward some postulates about the model of an atom. Bohr and Berry suggested the distribution of electrons into different orbits of an atom.